Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. To discover and recover, otherwise undiscoverable and unrecoverable crude oil and natural gas, and to do so from the Niger-Delta region of southeastern Nigeria, demands that we cross new frontiers in extreme-scaled algebra and high-performance supercomputing. Algebra is the elephant in the room that must be conquered before we can solve today's toughest problems that arise in physics, mathematics, and computing. Algebra is the recurring decimal and the common denominator at each processor that outline the massively parallel processing supercomputer. For example, the community atmospheric model has 530,000 lines of code and has algebra at its most computation-intensive core. My contributions to algebra are these. I invented how to solve the toughest and the most important problems arising in algebra, such as the community atmospheric model. I invented how to solve the most large-scale system of equations of algebra and how to solve them across a new internet that is a new global network of 65,536 tightly coupled processors that shared nothing between each other and that were already available in the market anyway. The computation-intensive mathematical problems that I emailed across my new internet consisted of a set of systems of equations of extreme-scale algebra that arose from my discretizations of a system of partial differential equations of modern calculus that also encoded a set of laws of physics. I experimentally discovered that massively parallel processing enables the extreme-scale computational physicist to solve the largest system of equations that arise in algebra, and that is the precondition to executing the most excruciatingly detailed simulations, such as the general circulation model that must be used to foresee otherwise unforeseeable long-term climate changes. My invention of the massively parallel processing supercomputer changed the way we look at the modern computer and became my contribution to the development of the computer. I am the subject of school reports in US schools because my invention of the massively parallel processing supercomputer has rich and fertile consequences for society. For me, Philip Emeagwali, my invention of how to massively parallel process the toughest problems arising in algebra was the culmination of my silent 16-year-long journey that began in the early morning of Thursday, June 20, 1974. My quest for the fastest supercomputer began in a small room that was upstairs of a White House at 195A Knox Street South, Monmouth, Oregon, of the Pacific Northwest region of the United States. I began my quest as a 19-year-old supercomputer programmer that was also a night janitor and a research mathematician in training. My mathematical quest predated the janitor mathematician in the Oscar-winning movie named Good Will Hunting that solved one of the toughest problems in mathematics. I was not on the cover of top mathematics publications because I was good looking. I was on the cover of top mathematics publications because I contributed to algebra and calculus and contributed to the existing body of mathematical knowledge that was written in algebra and calculus textbooks. Namely, I invented how to solve the toughest problems arising in algebra and calculus. I did my supercomputer research nearly every day, including Christmas days. For me, another public eureka moment resolving the timer issue occurred during the 16-hour marathon of massively parallel processing supercomputing session of the Christmas day of 1989. On that Christmas day, I was massively parallel processing across my ensemble of 65,536 processors and doing so in Los Alamos, New Mexico, United States. I visualized and programmed that new supercomputer as a new internet that I had theorized as a new global network of 2 raised to power 16 tightly coupled processors that shared nothing between each other and that were already available in the market, and that is the fastest computer de facto. Earlier, on the 4th of July 1989, I experimentally discovered how to massively parallel process my 64 binary thousand processors that were within my new internet, and how to parallel program them to compute together and do so as one cohesive, seamless supercomputer that was the precursor to the modern supercomputer. Shortly after Christmas Day of 1989, the Computer Society of the IEEE, that was the world's largest computer society, issued a press release stating that I, Philip Emeagwali, had achieved a breakthrough in massively parallel processing supercomputing. The IEEE is the acronym for the Institute of Electrical and Electronics Engineers. In the May 1990 issue of this academic journal named Software, the Computer Society of the IEEE described my experimental discovery of the massively parallel processing supercomputer as follows. The amount of money, quote, the amount of money at stake is staggering. For example, you can typically expect to recover 10% of a field's oil. you can improve your production schedule to get just 1% more oil, you will increase your yield by $400 million, unquote. That 1989 press release that announced my invention of the massively parallel processing supercomputer and the companion article published by the IEEE led to cover stories in mathematical publications and to mathematical stories on my mathematical discoveries, and in particular, mathematical stories on my contributions to new algebra and new calculus. My contributions to algebra and calculus was the front page story of the June 1990 issue of the Siam News. The Siam News is where newsworthy discoveries in research mathematics are announced. The Siam News is where new contributions to mathematics are described by research mathematicians and explained to research mathematicians. The Siam News is where new contributions to mathematics is recorded and archived for the Society of Industrial and Applied Mathematics and archived for future generations of research mathematicians. My contributions to computational mathematics was also the headline stories in newspapers across the United States, Europe, and Africa. Unlike the American or European research mathematician and scientist, I was never formally taught how to do mathematical and scientific research. I did scientific research at the science fair level and at age 15 in June 1970 in my one-room study that was near the intersection of Venn Road and Iweka Road, Onitsha, East Central State, Nigeria. In 1972, the science column of the Daily Times, that was then the national newspaper of Nigeria, mentioned a 17-year-old Philip Emeagwali of Christ the King College, Onitsha, East Central State, Nigeria. In the United States, I began solving the most extreme scaled problems arising in algebra and arising from the discretization of the partial differential equation of modern calculus. I began solving those algebraic equations on sequential processing supercomputers. I began solving those extreme scaled problems on Thursday, June 20, 1974 at 1800 Southwest Campus Way, Corvallis, Oregon, United States. 3 weeks after I began supercomputing, a newspaper that circulated in the cities of Monmouth and Independence, Oregon, United States, published a photo of a 19-year-old named Philip Emeagwali on its cover. Looking back to the early 1970s, I learned a lot in my first 16 years onward of March 24, 1974 in the United States. But I also spent 16 years on learning the sequential processing supercomputing that I learned from American computer scientists. I found my supercomputing vision in the early 1980s, and I found it at the farthest frontier of the massively parallel processing supercomputer. I learned that the answers to the biggest questions don't come easy. I'm Philip Emeagwali. My invention of the massively parallel processing supercomputer was written across major US newspapers, such as in the June 20, 1990 issue of the Wall Street Journal. That invention of a new internet, that was a new supercomputer and a new computer, was the exclamation mark of my intellectual journey that began in June 1970 and began in a bookstore that was near Zig's Roundabout in Onitsha, East Central State, Nigeria. And that was a shouting distance from Dennis Memorial Grammar School, Onitsha, Nigeria. My mathematical journey to the farthest frontier of calculus began with the 568-page blue hardbound book. That book was titled, quote, An Introduction to the Infinitesimal Calculus, unquote. That book was subtitled, quote, With Applications to Mechanics and Physics, unquote. That book was written by G.W. George William Count. My scientific quest for new physics also began in June 1970 and began in Christ the King College, Onitsha, Nigeria. My scientific journey to the frontier of knowledge of the most extreme scaled computational physics began with the 1,118-page book that was titled, quote, Advanced Level Physics, unquote. That physics textbook was written by Michael Nelcon and Philip Parker. Advanced Level Physics was the most popular physics textbook across the British Commonwealth. Advanced Level Physics was widely used in Nigeria, India, and the United Kingdom. I spent the 20 years onward of June 1970 mastering algebra and calculus and physics, and doing so to arrive at the frontiers of knowledge of algebra, calculus, and physics. I spent those 20 years trying to figure out how to solve previously unsolved problems in calculus and in algebra and in computing. I spent those 20 years researching how to solve the toughest problems arising in extreme scale computational physics, and in particular, how to execute their floating point arithmetical operations and execute those operations at unheard of speeds and execute those calculations across a new internet that is a new global network of processors that emulates the fastest supercomputer. I spent those 20 years in quest for new frontiers of technological knowledge. I spent those 20 years crossing those frontiers of knowledge. I spent those 20 years inventing how to solve the toughest problems that arose in the most extreme scaled computational physics. The common denominator of those grand challenge problems in supercomputing was that each problem had the largest known system of equations of algebra at its computation-intensive granite core. That invention of how to massively parallel process and how to solve the toughest problems arising in calculus and algebra, or how to process many things or processes at once, is my contribution to the future editions of the textbooks that I studied in 1970 and to textbooks such as An Introduction to the Infinitesimal Calculus that I studied in 1970 and to textbooks such as Advanced Level Physics that I also studied in 1970. A Nigerian student asked me, why do I have to learn algebra? I can give 1,001 reasons while algebra should remain the recurring decimal in the syllabus of the West African Examination Council called WAEC, or why algebra should remain in the syllabus of the Nigerian Joint Admission Matriculation Board called JAMB. The first reason all Africans should learn algebra is that algebra was invented in Africa and invented by African mathematicians. The first quadratic equation was first used in North Africa and first used centuries before the birth of Jesus Christ. That is, the quadratic equation is in the ancient algebra textbook of ancient Africa. So learning ancient algebra for WAEC or JAMB examinations is akin to learning ancient African history for WAEC or JAMB examinations, and it is akin to learning who you are and what your African ancestors contributed to mathematical knowledge. Just as the baby must learn to crawl before running, ancient algebra, such as the quadratic equation, must be understood before modern algebra, such as solving the world's largest system of equations and solving them across millions upon millions of processors, could be understood. As the leader in the supercomputing of tomorrow, the extreme scale algebra student in Nigeria should be trained to use her knowledge of extreme scale algebra to help grow Nigeria's economy, and in particular, to use her knowledge of how to solve the most extreme scale problems arising in modern algebra and how to solve those computation-intensive mathematical problems and solve them in parallel or by processing many algebraic problems or algebraic processes at once. As the leader in the mathematical sciences, the modern algebra student in Africa should be trained on how to solve the toughest problems arising in extreme scaled algebra and how to solve them on the fastest massively parallel processing supercomputers, and how to use that knowledge of extreme scale algebra to increase Nigeria's petroleum revenue. As I explained in detail in my lecture series that I posted at Emeagwali.com, a system of zillions upon zillions of equations of algebra must be solved by each oil company that is searching for crude oil and natural gas in Nigeria. It is, in part, for that knowledge of extreme scale algebra that Shell Oil Company keeps 40% of Nigeria's oil revenue. If Nigerians have the knowledge of extreme scale algebra and as well as have the knowledge of cutting-edge petroleum techniques and technologies, Nigeria will be on its way to keeping 100% of its petroleum revenue. Keeping 100% instead of 60% of petroleum revenues effectively doubles Nigeria's national wealth. A young Nigerian asked me, why must algebra remain in the school syllabus of Nigeria? My answer is that the mastery of extreme scale algebra is needed to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas from the Niger-Delta region of southeastern Nigeria. Put differently, the petroleum-based economy of Nigeria is in the hands of the modern algebraist in training and in the hands of the 9-year-old Nigerian that can only solve the quadratic equation of algebra. 20 years later, that 9-year-old Nigerian could be solving the most extreme scaled problems arising in algebra and solving those mathematical problems to help Nigeria use the massively parallel processing supercomputer to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas. In early 1964, and at age 9, I was enrolled in St. John's Primary School, Abo, Midwest Region, Nigeria. It was in 1964 and in Abo, Nigeria, that I learned the algorithm for finding the greatest common divisor. But in our home along Benoba Road, Abo, Nigeria, my father, Nnemeka James Emeagwali, taught me how to solve the quadratic equation of algebra. My father taught me algebra using his high school algebra textbook that was originally published in 1932 in the United Kingdom. My father used that algebra textbook at Christ the King College, Onitsha, in the British West African colony of Nigeria. Christ the King College was a famous Irish high school that my father attended for the 6 years, inclusive from 1942 to 47. That book, titled Advanced Algebra, was written by Clement Vavassor, C.V. Durrell. I learned the quadratic equation in 1964 from Advanced Algebra. I learned the quadratic equation 2 decades after my father learned it from Reverend Michael Flanagan, who also taught at Blackrock College, Dublin, Ireland. Blackrock College is one of the most prestigious schools in Ireland. Back in 1964, in Abo, Nigeria, I learned that solving the quadratic equation of algebra has something in common with cooking egusi soup, that is Nigeria's national dish. Solving the quadratic equation and cooking egusi soup both demands a foreknowledge of the algorithm for solving the quadratic equation and for cooking the egusi soup, respectively. At our outdoor kitchen at Bonoba Road, Abo, Midwest Region, Nigeria, I learned the algorithm for cooking egusi soup. That algorithm required a foreknowledge of the instruction that instructs the cook to add bitter leaf at the beginning, to add dried mangala meat a few minutes later, and to add fresh catfish towards the end. As a research supercomputer scientist in the United States, I solved the toughest problems that arose in extreme scale algebra, and I solved them in the step-by-step manner that I cooked egusi soup in Nigeria. Each partial difference equation of extreme scaled algebra that approximated its companion partial differential equation of modern calculus that encoded a law of physics and that I emailed to each of my ensemble of 65,536 tightly coupled processors, with each processor operating its own operating system, and with each processor having its own dedicated memory that shared nothing between each other, was my precise set of instructions. That's a general solution to my system of equations of extreme scale algebra that approximated my systems of equations of modern calculus, that encoded a set of laws of physics. To push the frontier of the fastest computer, and thus to invent a never-before-seen computer, was to harness the massively parallel processing supercomputer and to use that technology to show that the impossible to compute is, in fact, possible to compute, and to do the impossible at a time everybody said that parallel processing will forever remain a huge waste of everybody's time. In my vision of the 1970s and 80s, to push the frontier of human knowledge of the fastest supercomputer was to simultaneously harness my 64 binary 1000 tightly coupled processors and to synchronously process my 64 binary 1000 problems, and to process those problems in parallel. What made the news headlines in 1989 and thereafter was that I invented how to process many things or processes at once. What made the news headlines was that I invented how to communicate synchronously and how to compute simultaneously and how to do both to enable a parallelized extreme-scaled computational physics code to be used to foresee the previously unforeseeable motions of fluids that enshroud the earth. What made the news headlines was that I invented how to solve the toughest problems arising in physics, calculus, and algebra. I invented how to solve the toughest initial boundary value problems and how to solve those problems across my ensemble of 65,536 tightly coupled processors that shared nothing between each other. I invented how to solve those grand challenge problems and how to solve them in real life instead of taking a lifetime to solve them. For my invention of the massively parallel processing supercomputer, I used a set of laws of physics as my common denominator across each of my 64 binary 1000 commodity processors that outlined my new internet and defined that internet as a new supercomputer that is a new computer and that is a new global network of 2 raised to power 16 processors that were already available in the market. I invented the fastest massively parallel processing supercomputer that an oil company can use to reduce the time to market, such as the time between the discovery of crude oil and natural gas in the Niger-Delta region of southeastern Nigeria and the recovery of that crude oil and natural gas. A set of laws of physics was common in my system of partial differential equations of modern calculus that evolved through my system of equations of extreme scale algebra, that evolved through my set of floating point operations of arithmetic that evolved through each of my processors and that evolved through my new internet. I visualize my new internet as my new global network of 64 binary thousand commodity processors, or a global network of as many identical computers. Extreme scale algebra is at the mathematical foundation of the excruciatingly detailed petroleum reservoir simulation that in turn provides a computational surrogate for crude oil and natural gas recovery scenarios. Those recovery scenarios enable the oil company to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas. Until my invention that occurred on the 4th of July 1989 and that occurred in Los Alamos, New Mexico, United States, until that invention, the vector processing supercomputer was the king in the world of computers. In the 1980s, the vector processing supercomputer was the king of the computer performance hill that was then under 1 billion calculations per second. My invention of the massively parallel processing supercomputer dealt a massive blow, dealt a massive heart attack from which the vector processing supercomputer never fully recovered. My invention of the massively parallel processing supercomputer gave supercomputer scientists a powerful tool to make scientific discoveries. The dream invention in the world of supercomputer research is to invent how to make computers extraordinarily fast. For me, Philip Emeagwali, that dream invention became a reality on the 4th of July 1989. That invention validated the modern computer. Thank you very much. Thank you very much.
Insightful and brilliant lecture.
I'm Philip Emeagwali.
Insightful and brilliant lecture.